Hello and welcome back to your Chem 4 lecture. This is an exciting one. We are transitioning out of the general chemistry portion of the class and into the organic chemistry portion of the class by talking about your chapter 11 on organic compounds. So we finished up the general chemistry part. We've got a very brief organic chemistry part, and we'll wrap it up by talking about biochemistry later on in the semester. But in order for us to understand biochemistry, we need to understand organic compounds. Now, you might ask yourself, why organic compounds? Why are they important? And why do we have like a whole section of our class devoted to them? As you can guess, organic, as it sounds like, comes from words that suggest life-like or from life. And the initial discovery of a lot of these organic compounds is living things. So this is where things, when chemists were trying to divide out, what kind of compounds there are in the world, a long time ago, before they even had atomic theory or anything like that, or all the elements, they recognized that chemicals that came from living things had different properties than chemicals that came from non-living things. Just think like the difference between a rock and, a person. So that's a pretty good example of inorganic versus organic. Now, organic is a wider variety of compounds. So that's no longer the case that organic compounds have to be from living material, but that name is kind of stuck. So the modern definition of organic compounds is that an organic compound is any compound that's made from carbon and hydrogen atoms. Now, they have to contain carbon and hydrogen atoms, but that's not exclusive. They can also have oxygen, and often do have oxygen, sulfur, nitrogen, phosphorus, or even a halogen, like chlorine, for example, or bromine. And while a lot of these are, and a lot of the biochemicals that we're going to talk about in the future chapters are organic, you find it all the time. Organic compounds all around you in plastics. Gasoline is an organic, a mixture of organic compounds. Many medicines are organic compounds because they interface with the body, which again is largely organic compounds. And then plastics and perfumes. I haven't mentioned plastics, but yeah. The way that we write them is, just so you know, the formula always stays in roughly the same order, where we start by writing carbon first, then hydrogen, and then from there we go up the ladder with electronegativity. Is how we would order it from there. So any other elements are going to be written after that. Okay, so what properties do organic compounds tend to have? Usually organic compounds are going to contain covalent bonds rather than ionic bonds. I don't think we're going to talk about an organic compound that has ionic bonds in it. It's a very rare scenario, and it's a very reactive type of compound. These tend to have very low melting points and also low boiling points. Or I shouldn't say very low, just normal kind of range of temperatures, low melting points and low boiling points when we compare them to similar or analogous inorganic compounds. Organic compounds tend to be flammable, so they undergo combustion. In other words, they catch fire. And also, organic compounds tend not to be soluble in water. So for example, if you take vegetable oil and you mix it with water, vegetable oil is an organic compound. It's made of the fats of whatever vegetable it comes from. And these are very nonpolar compounds, and those nonpolar compounds don't mix with the polar water molecules down here, so they tend to stick together. And you see, it's not mixing here, even though you're pouring it into the water. Okay, so now comparing organic and inorganic compounds is very useful here at the beginning, so that we kind of understand, what is the importance of organic compounds. Inorganic compounds, that's anything that doesn't contain carbon, basically. These are usually going to be ionic, with some exceptions. Water, for example, is an inorganic compound, doesn't contain carbon, but it only has hydrogen and water, yet it has covalent bonds. That's also the molecular compounds that we were talking about in the last chapter, like ammonia, PCl3, those kind of things that we use the molecular nomenclature system for. They do contain covalent bonds. But most inorganic compounds tend to be, mixtures of metals and nonmetals, like sodium chloride, for example. These tend to be soluble in water, and they don't burn in air. So that's kind of one thing that we want to point out here. Propane which is C3H8. That's an organic compound, and of course, it is used as a fuel in, whether as a pure propane gas or sometimes in mixtures like natural gas. And then compare that to salt. Salt, of course, doesn't burn, and it does mix in water, whereas propane, first off, it's a gas, so it has a very, it has a low boiling point. It's a gas at room temperature, whereas salt is a solid at room temperature. Okay, so this is kind of a big table of comparisons here, but this is just kind of an example here. So again, organic compounds, their melting points are usually low, and the boiling points tend to be pretty low compared to inorganic compounds, which tend to have usually high boiling points. Now, there's a lot of variation here. So in other words, there's inorganic compounds with very low melting and boiling points, like for example, dinitrogen. N2 gas is technically an inorganic compound, yet its boiling point is, I don't know, like 77 Kelvin, I want to say. So it's very, very low, so negative almost 200 degrees Celsius. Yeah, so that compares with organic compounds, which given similar molar masses, they tend to have, again, much lower melting points and boiling points. Okay, so sample exercise number 1. I don't have the PDF ready for this yet, but hopefully I'll have it up soon. But you can follow along here. Identify each of these characteristics as most typical of compounds that are inorganic or organic. So we got A through F here. High melting point for A, not soluble in water for B, giving a formula here for C, another formula for D, E, talking about combustion or burning, and then F, talking about covalent bonds. So go ahead, pause the video. When you come back, we'll take a look at the answers together. All right, okay, let's take a look. So high melting points are associated with inorganic compounds. Not soluble in water usually is an organic compound. This formula here, CH3, CH2, CH3, if we added this all together, is the molecule propane again. So C3H8, that's organic, just composed of carbon and hydrogen. MgCl2, well, there's no carbon there, so that's an inorganic compound. It burns easily in air. That's an organic compound. They tend to burn very readily. And then finally, covalent bonds, we know that's typical of organic compounds. Okay, so now we're going to talk about a subclass of organic compounds. And this is how we're going to build it out. So we've talked in general about organic compounds. Now we want to talk about specific subclasses of organic compounds so that we understand, we can kind of build up our knowledge from here. Because there's a few different rules, and especially for nomenclature purposes, we're going to try to build it up slowly. Okay, hydrocarbons are a specific subclass of organic compounds, and it's exactly what it sounds like. Hydrocarbons are molecules that only contain carbon and hydrogen. So no oxygen, no nitrogen, no nothing, just carbon and hydrogen. So for an organic molecule, this is what's interesting about organic chemistry compared to what we've been seeing before when we did Lewis structures. Every carbon is always going to have 4 bonds. So in this case, if carbon is only having single bonds and it has, it's always going to have 4 bonds to whatever's around it. If we only have 1 carbon and we have 4 hydrogens, the carbon's in the center and it's bonded to 4 hydrogens. Now, in this case, and in this case down here, we only have single bonds in this hydrocarbon. So this is what we call a saturated hydrocarbon. In other words, there's as many hydrogens that can fit on the molecule as possible. Whereas if we had a double bond, which is what we're going to talk about in the future, that's what we're going to call unsaturated hydrocarbons. But let's focus on the saturated ones for now. Okay, so this up here, this is our first molecule here. And this is a organic compound that contains just 1 carbon. And this 1 carbon with 4 hydrogens here, this molecule is called methane. Now here we get 2 carbons. So we get 1, 2 carbons. And each of those is bonded to, they're bonded to each other. And then they're bonded each to 3 hydrogens. So in other words, there's no double bonds in this molecule. This is again a saturated hydrocarbon. And we call this molecule ethane. And don't worry, we'll have a table with all of these in the future. Now, there's a few different ways that you can represent these compounds, we want to kind of like show how this works here at the beginning, because we're going to see a lot of these organic molecules as we go through. So for methane, we saw it on the previous page here. This is what methane looks like. Now, the reason that we drew it that way is because we know that for methane, we've got a central carbon that's bonded to 1, 2, 3, 4 atoms. That means that it's got a molecular geometry of tetrahedral, and therefore has 109-degree bond angles from hydrogen, carbon to hydrogen. So this is our Lewis structure here, right? So now the Lewis structure is just a way of showing kind of the electronic representation here. And when we actually want to apply it to a geometric form, what we're going to do is we're going to use what's called the ball and stick model. So, or no, I'm sorry, the wedge dash model that we're showing here. So here, there's the easy ones to do, which is we've got hydrogens in the plane of the screen in this case. And that's easy enough to do. This is a tetrahedron. We're going to play around with these in lab as well. But this is a tetrahedron. We've got 2 of them that we can draw in the plane right here. But now, if we try to draw the other 2, we can't have it set up so that it represents a 109-degree bond angle without going into 3 dimensions. So that's what we do. We draw a wedge that looks like this. Now, this wedge is just a single bond, just like these other 2 here. But what it's representing is, it's representing that this bond is coming out of the screen towards you. So it's like coming out at you, okay? And then we have a dashed wedge, which looks like this. Now, this is the opposite. This is going into the screen away from me. So, or sorry, so towards me, I guess, in this case, right? So it's coming into the screen towards you or towards me. Now, oops, sorry, hold on. There we go, and there we go. So what you need to do is you need to get good at being able to visualize these in your head, where this bond coming out of the page towards you, and then this bond going into the page away from you. The more you have practice with this, the more you're going to feel comfortable. And there's some good practice on the homework as well with this. Okay, that's our wedge dash model. Now, this is important because that's what you're going to have to draw in the future. So that's why I kind of spend a lot of time on it here. The ball and stick model is a good representation because it's easy to see, oh, we have a carbon bonded to 4 hydrogens. That's really easy to see. And again, you see the 3-dimensionality here where it appears tetrahedral, which is good. Space filling is more useful for biomolecules. So we're going to talk about that later. But for now, we're going to focus on this wedge dash model. Okay, so that's methane, right? And methane is saturated. It's just got a single carbon with 4 hydrogens. Ethane is our next one, okay? And with ethane, what we have here is we have 2 carbons, so they're bonded together. And you can always assume that when you have multiple carbons, they're going to be bonded together somehow. In this case, we only have 2, so that's easy enough, right? We just know, okay, it's carbon bonded to carbon. Now we know that each carbon also has to have 4 total bonds. So we're missing 1, 2, 3 here on this carbon, 1, 2, 3 here on this carbon. And that fits because we have 6 hydrogens. So it's 1, 2, 3, 4, 5, 6 hydrogens. So that gives us our C2H6. Now, in this case, I'm not going to try to draw this out here. This is getting a little confusing here, right? Where you have multiple carbon centers to kind of take into account here. It's difficult to keep track of what's coming towards you and what's coming away from you. We'll have more time to play around with this when we get to lab. But yeah, so this kind of gives you the same idea of the representations here. Okay, so given all of that, if you have a butane molecule here, try to predict the shape around each carbon. So let's just try to like draw it out. So we've got 1, 2, 3, 4. And let's just review real quick. Remember methane, because methane, the carbon in the center is bonded to 1, 2, 3, 4 hydrogen atoms, so 4 bonded atoms. That's a tetrahedral geometry. Ethane, we have 2 carbons, right? So let's look at the first one first. This carbon is bonded to 1, 2, 3, 4 other atoms. So carbon 1 then is tetrahedral as well. Okay, and then let's look at carbon 2. This carbon is bonded to 1, 2, 3 hydrogens and 1 carbon. So that's 4 total bonded atoms. No lone pairs. So that's tetrahedral as well. Okay, so given that, guess what the geometries for each of these 4 carbons are going to be? Or don't guess, you know how to do this, so you can do it. Come up with the answer and pause the video, or pause the video and come up with the answer, and then we'll talk about it together here when we get there. So pause. Okay, we're back. All right, now, no big surprise here, right? Each of these has 4 covalent bonds. So that means each of them is going to be tetrahedral in geometry. Okay. Now, methane and ethane and butane, what we just looked at, are all examples of what we call alkanes. And these alkanes are saturated hydrocarbons. So an alkane is, so this is kind of another word for basically saturated hydrocarbons. So we know we have a alkane when we have no double or triple bonds. Okay. Right. Okay. So now what we're going to do is we're going to talk about the naming system for these. So this naming system is a little bit different than what we learned before for inorganic molecules. So we're going to try to explain it here. Hopefully it's a little bit simpler is the goal. And we're not going to get too deep in the weeds. Of course, there's complications that we can come up with, but this is a 18 chapter course, so we're not going to push too hard with this necessarily. We've got alkanes. Okay, so we already mentioned this, right? Alkanes are saturated hydrocarbons. We have a continuous chain of carbon atoms, so that means it's uninterrupted. They have to be named using an IUPAC system. So we learned previously the IUPAC system for nomenclature for ionic compounds. Now we're doing the same thing for organic compounds. Now the names are all going to end in A and E. So like methane and ethane, we've already learned. Butane, we've heard. So let's go ahead and take a look, because I don't know how else to explain. So if you have 1 carbon in your alkane, that's methane. If there are 2 carbons in your alkane, that's ethane. And that's what we've seen so far. Now 3 carbons, we already talked about it. That's propane. Oof. Whoa, 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 whoa. Okay, hold on. There's a big mistake here. Big mistake here. Okay, hold on. Jeez. So, okay. So I don't know if this is the way it is in the book. I'm gonna have to double check this, but these are each a line off here, because this is important that we want to talk about these line angle formulas. Oh yeah, okay, I see. Okay, great. Okay, so we'll take another look here, but I kind of see what they're doing here. They kind of ran out of space over here because the molecules are too condensed. But okay, so methane we've looked at is 1 carbon in the alkane, that's CH4. 2 carbons in the alkane, that's when you have ethane. 3 carbons, propane. 4 carbons, butane. Okay, so the first 4, you basically have to memorize. I don't think there's any system that I know of anyway, where you get meth for 1, eth for 2, prop for 3, and but for 4. But then after we get to 5, now we're in the Greek prefix name. So 5 is pentane, just like we know penta, right? 6 is hexane, 7 is heptane, 8 is octane, 9 is nonane, and 10 is decane. So in other words, you have 10 carbons in your alkane. That molecule is named decane. 9 is not. 8 octane, et cetera, et cetera, et cetera. Now the line angle formula, I want to say that we've got, let me tell you, okay, we are going to get there to the skeletal formula here in a little bit. I just want to point out here that this first one up here actually represents ethane, okay? And then this one is propane. Yeah, I kind of see things get a little tricky here. But basically there is no line angle formula for methane is what I want to point out at this moment. And we'll talk about the line angle formula in just a bit. Okay. All right, now let's talk about the different types of formulas and the ways that we've been writing it, even in this chapter, even right before now. So sometimes we just show you things and see if it makes sense. And now we're going to try to explain it to you. So the first one that we want to talk about is what we call the condensed structural formula. So in a condensed structural formula, each carbon atom and the hydrogen atoms that are attached to it are written as a group. And of course, this group is going to be multiple hydrogen atoms usually. So you subscript the number of hydrogen atoms here. So like, for example, for butane, we know that its butane is 1, 2, 3, 4 carbons, and each of those is saturated, right? So it has a total of 4 bonds. We fill that in with our hydrogens. So we fill it in with our hydrogens like that. Okay, and then what we're going to do is, when we condense it, we basically think of this carbon as the first group in the condensed structural formula. So this one, it's the carbon bonded to 3 hydrogens, that becomes CH3. This second carbon is a carbon bonded to 2 hydrogens, that becomes CH2. The third one as well is bonded to 2 hydrogens, that becomes another CH2. And then the fourth one here is bonded to 3 hydrogens, so that becomes CH3. Now, the reason that we do this is because, as you can see, it gets really tedious to draw all of these hydrogen bonds. And the one thing you'll notice about hydrogen or organic compounds is they have a lot of hydrogens. So ultimately, we're just going to ignore the hydrogens is what we'll find out. For the condensed structural formula, we just limit it to saying, okay, this carbon has 3 hydrogens bonded to it. This carbon has 2 hydrogens bonded to it. This one has 2 bonded to it. And this one has 3 bonded to it. Okay. So now you can expand it to show what we did here. So this is the expanded structural formula. What I drew up here. And this is the condensed down here. Again, condensed structural formula. And that just works to save space. Yeah, I mean, even just check it out. This is CH3. Well, you can just write it as CH3. And we'll just interpret it in our brains. When we see the CH3, we know, okay, it's a carbon bonded to 3 hydrogens that's then bonded to another carbon. Okay, now, we also have molecular formulas. That's the total number of carbon hydrogen atoms. That's easy enough. Now, the big one that we want to learn is line angle formulas. So whenever you see organic chemistry represented in popular culture, you're going to see big structures of just lines that are connected together. And these lines that are connected together are line angle formulas. So it's a way of representing very complex molecules in a very visual manner. So that's one of the goals of this class, is helping you read line angle formulas so you can understand a little bit about a molecule just by glancing at it. Now, what we do in this case is, so remember our condensed structural formula was like this: CH3, CH2, CH2, CH3. Now we know that each of these bonds, this has got to be a 109-degree bonding. Same thing here. Here, that's 109, and up here as well. Okay. But that's not really shown in this straight chain. So this is not giving us a good representation of what that is. So that's where the line angle formula comes in. Now, in the line angle formula, we actually are just going to get rid of the CH2, CH2, CH3 altogether. We're going to write carbon 1 as our first carbon. That's just a dot. We don't even care about the hydrogens anymore. They're gone. Okay. Now, draw it to carbon 2. We're going to start by draw an angle like that. Okay. Now, we're going to draw it at an angle. This is carbon 2. Now, carbon 2 connects to carbon 3, and we're going to draw that at an angle. And we just want this angle to roughly represent 109 degrees. Doesn't have to be perfect. We're just doing our best. And then finally, this is connected to our fourth carbon, which is not connected to any more carbons. So that's where we end our line angle formula. So again, here what we do is we only show the carbons. Okay, so we only show the carbons, and each carbon is at a corner or at the end of a line. So we got 1, 2, 3, 4 carbons. Now you might ask yourself, aren't we omitting a lot of information here? And the truth is, we're not really omitting that much. The only thing that we're not showing is the hydrogens that are bonded to the carbon. But looking at this line angle drawing, if we know that this is a carbon, this is a carbon, this is a carbon, this is a carbon. First off, we know that there are 4 carbons involved there, and all the other atoms are hydrogens. Because if there was anything else like an oxygen or a nitrogen, we'd have to write that. So we only have 4 carbons, and therefore all the other atoms are hydrogens. So that has to be butane, right? It's a 4-carbon alkane. There's nothing else there. So it's just butane, easy enough. And then you might ask yourself, well, how do I know how many carbon or how many hydrogens are bonded to each carbon? Well, we know each carbon has 4 bonds. So look at this first carbon, carbon number 1. I'll call this carbon 2, and then 3, and then 4. Carbon 1 is only bonded to carbon 2. So that's 1 bond. But we know carbon has to have a total of 4 bonds. So we take 4 minus 1, and that gives us 3. So we know that this first carbon has to be bonded to 3 hydrogens. There's 3 hydrogens that are just not shown there because, again, they take up a lot of space, as we're about to find out. They don't really do that much. Now, carbon 2, on the other hand, is bonded both to carbon 1 and carbon 3. So carbon 2, we know, has 4 total bonds because it's carbon, okay? And we know 2 of them are bonded to carbons, other carbons, carbon 1 and 3. Therefore, the other 2 bonds on this carbon have to be to hydrogen. So therefore, you have 2 hydrogens. So you see, we're not losing much information. And in fact, we're making it a lot easier to draw the molecule and a lot easier for us to interpret the molecule as well. It's just a matter of learning the language. Once you learn the language, you'll find that it's really easy to do. Okay, so yeah, so we mentioned already how these alkanes can be represented. There's the molecular formula, ball and stick model, expanded structural formula, condensed structural formula, and now finally the line angle formula. And this is an example of butane. So butane's expanded structural formula shows that we have 4 carbons in a row, right? C4H10. So that's its molecular formula. Then we've got 1, 2, 3, 4 carbons in a row, CH3. If we want to condense it, we can go to CH3, CH2, CH2, CH3. And you can do all these funky things with the condensed structural formula. Of course, most of the time, you're just going to be drawing it in a line. I don't think there's any reason that you would do this. And then to condense it even further, we can go to the line angle formula, which again only represents the carbons at the endpoints or at the angles. Okay, so here we go. Go ahead and give me the, given this expanded structural formula, give me the molecular formula, the condensed structural formula, the name, and let's just do this now. What are we waiting for? The line angle formula. Okay, so give it a shot and pause the video here, try to work on these, and then when you come back, you'll have the answers together, okay? So pause. Okay, I'm gonna assume you paused and you worked on it, and now you're ready to go. So let's go ahead and take a look at it. The molecular formula is easy enough, right? We can count, there's 1, 2, 3, 4, 5 carbons. So that's C5, no problem. Now the H's, we got 3 plus 2, so 5, 7, 9, 12. So that's C5H12. Cool, easy enough. Next up, the structural form, or the condensed structural formula. This is the expanded structural formula. To condense it, what we're going to do is this carbon is bonded to 3 hydrogens, so that's CH3. That's bonded to a carbon that's bonded to 2 hydrogens, CH2. The next one is 2 hydrogens again, then 2 hydrogens again, and then finally 3 at the end for the 5th carbon. That's what our condensed structural formula looks like. What's the compound name? Did you come up with it? Well, this is the 5-carbon compound, 5-carbon alkane, and we call that pentane. Finally, the line angle formula. This is easy, watch this. So carbon 1 goes up to carbon 2. Oh, geez. goes down to carbon 3. Oh, geez. I don't know. I think I got something up with my, my clicker here. I think I'm like, wait, taking too long. So carbon 1 goes up to carbon 2, down to carbon 3, up to carbon 4, down to carbon 5. And that's your line angle formula. Okay. All right. So now why don't you go ahead, pause the video again, give me the condensed structural formula, and let's go ahead and do the line angle formula now too, because I feel like you should get good at that. The sooner you're good at that, the better off you. So pause the video here, and when you come back, we'll take a look at the answer. So pause. Okay, and we're back. So ethane is easy enough. It's CH3, CH3. Heptane, 7 total carbons, right? Hepta is 7. So there's a CH3 on each end, and then 5 CH2s in between. Now, for the line angle drawing, ethane is really interesting. It's just a line. You got carbon 1 and carbon 2. Heptane's more fun. It's, you start at carbon 1, go to carbon 2, carbon 3, 4, 5, 6, 7. And there's your line angle formula for heptane. Okay, now, alkanes do have one different rule, or there's a different thing that you can do with alkanes that happens sometimes and can be very useful in certain contexts, which is some of them can actually form what we call rings or cycles, starting from a 3-carbon cycle. So starting from cycloalkanes, or starting from propane, C3, H8, we can have a line angle formula like this, so carbon 1 to carbon 2 to carbon 3. Now, there also exists a cyclic form where carbon 1 is bonded to carbon 3. So this is propane over here. And then cyclopropane has carbon 1 bonded to carbon 2 like before, bonded to carbon 3, and then bonded again to carbon 1. This is cyclopropane. And yeah, the way that we note this is, okay, first off, we should note the chemical formulas here. Because we have this extra carbon-carbon bond, we actually have 2 fewer hydrogens in cyclopropane compared to propane. Okay, and the way that we name it then is we just use the word or the prefix cyclo in front of the name of the alkane. So propane, when it's in the cyclic form, becomes cyclopropane. Okay, so starting at carbon 3, you can have more cyclic alkanes above that, but the most common ones are going to be basically 5 and 6, so cyclopentane and cyclohexane. So cyclopropane exists, cyclobutane exists, cyclopentane is very common, and cyclohexane is very common. So now note, each of these, the line angle formula is just a geometric shape. So it's one of the, the regular shapes, I want to say. Gosh, I have not learned that in a long time, but note we have an equilateral triangle, then a square, followed by a pentagon and a hexagon here. And because each of these is just a carbon bonded to itself over and over again, of course, each of the lengths are the same. So these are our most common cycloalkanes. Okay, so let's go ahead and try to name these, given the IUPAC names for each of the following, A and B. Pause the video here, try to think it through, and when you come up with your answers, let's go through it together. So pause. Okay, so for the first one up here, it's a straight chain alkane, so it's not cyclic. That's important. So let's count up the number of carbons that we have. 1, 2, 3, 4, 5, 6, 7, 8. So an 8-carbon alkane is called octane. Okay, now down here, we have 5 carbons in a ring. 1, 2, and it's useful in a ring to start where you number from. Otherwise, go around and around in circles a little bit here. So we have 5 total carbons in this ring. And that means that it should be a pentane, right? 5 carbons. And because it's cyclic, we call it cyclopentane. Yeah. There we go. Okay, so let's give it a little bit more try. Go ahead, pause the video again, work on sample exercise number 6 here. Give me the names of the following alkanes, A, B, C, and D. Pause the video, and when you come back, we will take a look at the answers. Pause. Okay, so hopefully you're doing good. You just have to count the number of carbons, right? So for A, 4 carbons in a chain, that's butane. For B, that's 3 carbons in a ring, that's cyclopropane. C has 8 carbons in a chain, that's octane. And then finally D, 6 carbons in a ring, that's cyclohexane. Okay, so now that's the easy part, right? Now, unfortunately, there is a slight complication here, which is that we don't always have straight chains for our organic molecules. In other words, there's no reason that this butane has to be arranged with carbon 1 bonded to carbon 2, which is then bonded to carbon 3, which is then bonded to carbon 4. And in fact, oftentimes we see branches in the chain, where here, this has the same molecular formula, but we've got 4 carbons and 10 hydrogens, but the middle carbon is actually bonded to 3 carbons. And so we have a CH group in the middle that's then bonded to 3 CH3 groups. So we're talking about how we name these here in a little bit. Now, this property where you have 2 molecules that have the same molecular formula, but they're different molecules because their arrangements are different, this is what's known as isomerism. And this is a very particular type of isomerism that we're going to talk about, which is structural isomers. Structural isomers are 2 molecules that have the same molecular formula, but crucially have a different arrangement of atoms. So the same number of atoms, but the atoms are bonded in a different way. Here we have butane, which is a straight chain alkane. And then down here, we have a branched alkane. So this is straight chain, is what we call it. And then down here, because you can't draw a single line that contains all of them, all of the alkane or all of the carbons, we call this a branched chain down here. Okay, now that presents us with a difficulty, which is how are we going to name it? So, okay, well, let's start with just a thought exercise. Given all of that, can you draw 3 possible structural isomers of pentene, C5H12? So note that you're starting with C5H12, that's 1, 2, 3, 4, 5 carbons, looking like that. Can you think of 3 different ways to arrange these atoms? This is kind of a fun thought exercise. It's almost like a puzzle. So give it a try, and we'll take a look at the answer when we come back. So go ahead, pause the video here. Try to draw these structural isomers similar to what we did here with butane and this other branch chain. Think how you can branch this molecule, and then we'll take a look at the answer when we come back. Pause the video, and then let's go ahead and take a look at it. Okay, so first up, just like we did with butane, the way you can think about it is, okay, well, let's take a carbon off the end and put it on the second carbon over here. So let's do that with pentene. So that's 1, 2, 3, 4 carbons in a row. And now we've got this group sticking off of the central atom. Okay, so that's pretty good. So we've got our first possible structural isomer, our second possible structural isomer. Now, here's the weird thing. You might think, okay, well, what if we do the same thing, but in reverse? So what if we take this guy and put it over here? That would give us this structure right here. Now, here's the problem. These 2 are the same. So they're not isomers now. If you just flipped it, you just imagine yourself flipping it in 3 dimensions, they overlap each other exactly. So in other words, these are the same molecule. So in other words, they're not isomers. Here, this is fine. These are isomers. So we have to think of another way to do this. So what I would do is, okay, well, let's go ahead and take the other CH3 over here and move it to this central carbon one more time. In this case, we get something that looks like this. So we have 1 central carbon that's bonded to 4 carbon atoms that are each bonded to 3 hydrogens. And sure enough, that is another isomer that we can have. So I hope you had fun thinking about that. It's like a nice little structural problem. And each of these are different molecules that have very different properties. So this is an important thing to consider when we're talking about organic chemicals. Okay. All right. So how do we name these molecules that have substituents, these branched chain organic compounds that have these substituents sticking off in the middle? Well, there's two types of substituents that we're going to focus on. And I just want to, I'll define it here. Substituents are atoms or groups of atoms that are attached to the main carbon chain. We have two different types. We have alkyl groups and halo groups. Now, alkyl groups are just what they sound like, right? Alkyl sounds like alkane, and sure enough, it is. An alkyl group is just a group of carbon atoms that's attached to the main carbon chain. And the way that we name it is by using the IUPAC system with an YL ending. So it's like we take the name of the molecule minus ANE and then plus YL. So think about it this way. If you have a single carbon, so let's look at one of the isomers we looked at here. Here we've got carbon 1, 2, 3, and 4. So we know that our main name is butane here. Now off of carbon 2, we have CH3. In other words, we have a 1 carbon alkyl group. Well, a 1 carbon alkane is methane, right? So we take out the ane, we add YL, and we get methyl. So in other words, this is going to be methyl butane. And in particular, we'll talk about this in the next, I just want to put this here now, it's 2-methyl butane, but don't worry about that. Okay. Now the other one that we have are halogen substituents. So halo substituents are halogen atoms that are attached to the carbon chain. They basically just take the place of one of the hydrogens. And of course, there's fluorine. If you have a fluorine as a substituent, that's fluoro group. Chlorine becomes chloro. Bromine becomes bromo. And iodine becomes iodo. Okay, so here's some more examples. So we've got the methyl group that we talked about. There's the ethyl group, which is just 2 carbons sticking off of it. If you have 3 carbons in a straight chain, that's a propyl group. If you have 3 carbons that are bonded to the middle carbon here to the main chain, that's what we call isopropyl. 4 carbons in a row is butyl. And then finally, there's this group here, which is isobutyl. It looks like an isopropyl with an extra carbon in between it and the chain. So just to give you an example here of an isopropyl group. So let's look at like a longer chain here. This is 1, 2, 3, 4, 5, 6 hexane. And we can imagine an isopropyl group coming off of this carbon here. And that would look like this. I think I did that okay. I think we have to add one more here just to be safe. But so an isopropyl group would look like this in line angle form. Similarly, isobutyl group. So let's go ahead and do a longer one here. And then in the middle of the isobutyl group, you have 4 total carbons. But the way they're bonded is you have carbon 1 here, bonded to carbon 2, and then carbon 2 is bonded to like 2 other carbon atoms here. Fluoro, chloro, bromo, iodo, those are no problem. Those are just literally a fluorine atom, a chlorine atom, bromine atom, or an iodine atom. Oops. Okay, so given all of that, go ahead and give the IUPAC name for the following compound. Did I tell you? Man, we didn't even talk about numbering. I don't even know how we're supposed to do this here. So, okay, so let's go ahead and do a couple more examples before we move on. So here, we're gonna do this one together, and then we'll do another example together as well, because I think the more examples you do, the better off you're gonna be. And we have a whole worksheet to do in class, so that's gonna be just fine. Okay, so now, for this one, wow. Okay, so when we come across a molecule that has substituents like this, the first thing that we want to do is identify the main chain. And this is going to be the longest chain of carbon atoms. So, and note that these have to be kind of in a row. So here we have a few different options, right? There's carbon 1, we'll just start from here and just kind of test it out. Okay, oops, hold on. Okay, here we go. carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So there's 5 carbons in a row there. Now we could also imagine going carbon 1, carbon 2, carbon 3, carbon 4, but then it would end at 4 carbons. So 5 carbons is longer than 4 carbons, so 5 carbons brings out. So we know that the first part of this name is pentane. Okay, number 2, we want to number the chain. So in other words, we want to number the carbon, number the carbons that are in the chain. So in other words, in this case, we got to be, carbon 1, bonded to carbon 2, bonded to carbon 3, bonded to carbon 4, bonded to carbon 5. And now here's the key. It doesn't have to be left to right. It could be right to left, or it could be however, our molecule is organized. Now in this case, we've got 2 different ways that we can number it. We can number it left to right. That's 1, 2, 3, 4, 5. Or we could number it right to left. That's 1, 2, 3, 4, 5. Okay. Now the way that we can choose between these 2 is that we want to have the substituents at the lowest possible number. So here we have 2 substituents. We've got a methyl group and we have a chloro group here. So I'm just going to write those out. We've got chloro and we've got methyl. Now, either way we number it, methyl is always going to be at carbon 3. But chloro here could either be at carbon 2 or carbon 4. Since we need the substituent to be at the lowest possible number, that means that we have to number it left to right 1 to 5, like what we see up top here. That means that the 5, 4, 3, 2, 1 is no longer acceptable as a possible numbering scheme, and then it has to be there. Okay, 3. So name substituents. So name the substituents, put the number of carbon they're bonded to, in front of their name. So here we've got 2 chloro, 3 methyl. So just so you know, they're listed in alphabetical order. So we'll put this here as well. So chloro versus methyl. Chloro is going to come first because it's C over M. Chloro is bonded to the second carbon. So we know that's going to be 2 chloro. So it's 2-chloro. Now we have methyl group on 3, so that's 3-methyl. So we'll put 2 chloro dash, so 2-chloro dash 3-methyl. And now this methyl is just going to run right into the main name of the chain here for a final name of 2-chloro 3-methyl pentane. So I know that was tricky, so let's go ahead and do some examples here. Let's make sure that I don't screw this up here. Again, number 1, give the alkane name for the longest chain. Number 2, number it. Make sure that you're starting from the nearest and nearest to substituent. And then finally, give the location and name for each substituent in alphabetical order as a prefix to the name of the main chain. Okay, let's go ahead and do another example here because I think there's a lot to talk about. Where's some clear space here? Okay, so let's do cycloalkanes and then we'll do the next one. Okay, for a cycloalkane, the rules are actually a little bit easier. When a cycloalkane has just a single substituent, all you have to do is put the name of the substituent in front of the cycloalkane. So here, this is cyclohexane with an ethyl substituent. Now, we don't have to number the chain here because it's just a ring, right? I mean, you just pick whichever number is number 1. In this case, clearly the one that's bonded to the ethyl group is number 1. So all we need to say is that this is a cyclohexane with an ethyl substituent, or just name it ethyl cyclohexane. So in other words, no number is needed if you just have a single one of them. Okay, so let's go ahead and I need like a blank slide here. Let's go ahead and do some naming here because I think otherwise it's a little confusing. So let's go ahead. We'll discard those. Hold on. We're going to put a new slide in. Perfect. Okay. Let's do some examples here. So let's go ahead and I'm just going to write out a couple of these here. Okay. And we're going to try to come up with some names together to make sure that we know what's going on. And just one more is going to be good. Okay, there we go. All right. So let's just start with these three. Now, if you're feeling reasonably comfortable with this naming scheme and you're ready to try this, go ahead, pause the video here. If not, please stick around and we're going to take a look at it together. Okay, so try to come up with your answers, but other than that, we'll try to come up with them together. Okay, let's look at the first one here. So we want to identify the longest chain. Now, starting from here, we'll just start left to right first because that's the simplest one, right? This is 1, 2, 3, 4, 5. Now you could also do 1, 2, 3, 4, 5. So those are tied. Now in this case, if you have a tie and there's no other clear way to make a decision, in other words, you don't recognize any other groups that you're worried about. For example, if there were a chlorine down here, then you definitely want to go this way because you have more substituents. In this case, it's an absolute tie. So it's really up to you which one you choose. And what's interesting is what you'll find is you get the same answer either way. You can also start up here. This could be carbon 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Either way, totally fine. Now, just to keep seeing things simple, we'll start just going left to right here. Since everything's tied, we can just choose left to right. That's easy enough, right? Okay, now let's identify our substituents. We've got a single carbon sticking out over here. That's a methyl group. And then we've got a 2 carbon substituent sticking out over here. That's an ethyl group. Now we know that we numbered it correctly going from left to right because the methyl is on carbon 2 this way. We would be on carbon 4 the other way. And the ethyl group is on carbon 3. So that's the same. Okay, so now we're ready to go ahead and number. So we start with our name. We know it's pentane. Okay, then ethyl versus methyl. E comes before M in the alphabet. So we start with the name ethyl. So that's 3-ethyl. And then methyl is on 2. So that's 2-methyl pentane. Okay, all right. Are you feeling good? Are you ready to try the next one without me? If so, go ahead, pause the video, write this in your notes, and then we'll come up with the answer together in a minute. If not, stick around. So first up, find the longest carbon chain. So this is carbon 1, 2, 3, 4, or vice versa. It could be 1, 2, 3, 4. But we know that our carbon chain has to be butane. There's no doubt about that. Now, here's the thing. Is it going to be, I guess I should have flipped this. Gotta learn how to draw other colors with this thing. Boy. There we go. So 1, 2, 3, 4, or is it 1, 2, 3, 4? So identify your substituents. We've got chloro up here and a bromine down here. That's a bromo. So it's tied, right? We've got 2 chloro or 2 bromo. So the thing that takes precedence here is alphabetical order. I don't know if this is going to come up on our exams. I'm trying not to make these too difficult. But in this case, because B comes before C, that means bromo gets priority. And so the correct numbering should reduce the number on the bromo. So in this case, it should be 2 bromo. So bromo comes before chloro, so that should be 2 bromo, 3 chloro, butane. And there you go. Okay, how are you feeling now? Are you feeling ready to tackle this one without me? If so, please give it a shot. If not, we'll stick around and we'll do it together. So let's go ahead and take a look at this. So again, the longest carbon chain first. That's going to be 1, 2, 3, 4, 5, 6, 7. And no doubt about this one, substituents are clearly favored over here on the left side with this iodine. So, okay, so 7, that's going to be heptane, right? And what's our substituents? Well, we've got an iodine, that's an iodo substituent. Then we got this weird Y-looking thing. This is the isopropyl group that we were talking about before. It's 3 carbons that's bonded in the second carbon to the main chain. Okay, so how do we label this? Well, it looks like iodo would come before alphabetically isopropyl. So we're going to call it 3 iodo, 4 isopropyl, heptane, just like that. And that's how we can name alkanes. Okay, now going the opposite way, drawing formulas is actually a little bit easy because the IUPAC name is going to give us all the information that we need. There's a lot of steps that we don't have to worry about, like numbering the carbons, because all of that has been done for us here. So let's take a look at this example. 1-chloro, 1,2-dimethyl heptane. Start by just starting from the end here, right? We know heptane is a 7-carbon chain. So let's go ahead and draw a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. Okay, now what are the substituents? Well, we have a chloro on 1, and we have methyl on 1. Oh wow, this is already a mistake here. Let's save the book a little bit of embarrassment here. Should be 2,3-dimethylheptane, we'll say. So carbon 1 has a chlorine group. Carbon 2 has a methyl group. And carbon 3 has a methyl group, like that. So this is something that we didn't see here before, but if you have multiple of the same substituent, the way that you name it is, you name it by using the prefix di in front of the name of the substituent to give you the number of substituents that you have. Could be 2 or 3, for example. In this case, we just have the 2 on carbons 2 and 3. So that's a methyl group here and a methyl group here. Okay, so go ahead and give me the condensed structural, or just give me the line angle formula for 3-bromo, 1-chloro, butane. Give it a shot, pause the video here, and then when you come back, we'll take a look at I'll draw the line angle for you, and we'll take a look at the condensed structural formula. But go ahead, pause the video, and when you come back, we'll have the answer. Okay, so butane is up first, right? So we're starting from the end. Butane is a 4-carbon chain. So that's 1, 2, 3, 4 carbons. Okay, now it says that we have a chloro on 1. So if this is 1, then we might as well number it left to right. We're going to put our chlorine right here. Then we have a bromo on carbon 3. Carbon 3 is here. Put a bromo right there. And that's all you have to do. Now, the structural formula, of course, you have to do a little bit more. You have to draw in the hydrogens. But just focus on the line angle drawing and you'll do a lot better. Okay. All right, let's go ahead and name each of these following alkanes. Pause the video here. And again, we'll work it through. I recommend really give it a shot now. Name these. And when you're ready, unpause the video and we'll be back with the answer. So pause. Okay. So looking at it here, we have a chloro on carbon 2 of a 1, 2, 3, 4, 5-carbon chain. That looks like 2-chloropentane to me. Let me just double check here. So pentane, all right, up here, 2-chloro, and then down here. Oh, I guess we're doing them at the same time, sorry. So I've got this as 2-chloropentane. Now down here, the substituents are on the left side. So let's start with this carbon here. That's 1, 2, 3, 4, 5. So again, it's a pentane. This time we have methyl groups on carbons 2 and 3. So that means that it's got to be 2,3-dimethyl pentane. Again, that's how we can represent that we have multiples of the same substituent. Okay, so 2-chloropentane and 2,3-dimethylpentane. All right, so we're almost ready to wrap up the lecture here. We're just going to talk about a few different properties of alkanes that you'll need to know about. Basically, these different alkanes have different properties that become extremely useful for different purposes. For example, if you put a waxy coating on a fruit, that helps reduce moisture loss from the fruit. and also keeps it nice and shiny. Okay, so if you have methane through butane, so methane, ethane, propane, and butane are all gases at room temperature, and these can be used as heating fuels. Basically, these are gases that you can use as like a natural gas is the way you can think about it, or propane gas. You burn it and then you get your heat or your fire from that. Alkanes that have 5 to 8 carbons are highly volatile liquids, and they're useful as fuels. So pentane and hexane in particular are really useful solvents in an organic chemistry lab. Octane is one of the main components of gasoline. So it's a really useful fuel that you can use to burn. Anything with 9 to 17 carbons, these are liquids that have higher boiling points, and they're more likely to be found in things like motor oils, mineral oil, so things with high viscosity that are really useful for like lubrication, for example. But they also include compounds that make up kerosene, diesel, and jet fuels. So again, you can burn them really well, but they can also be used as lubricants. Anything with 18 or more carbon atoms are waxy solids at room temperature, which would include Vaseline, which is called petroleum jelly. Okay, alkanes are famously nonpolar and they're insoluble in water. So like, for example, this is an oil spill. There's recently one right outside of our Orange County beaches where a lot of these organic compounds come out of the ground and they mix with the water, or they don't mix with the water, and keep this slick oil surface that can be really problematic. They're less dense than water, so they float on top of water, insoluble, so they're not mixing in. They are flammable, so they can burn very easily. And yeah, this also comes from crude oil. So again, this could be a picture out of the news from recent times, where you get this thin layer of crude oil on the surface. Okay, combustion. Now, we talked about combustion reactions before, but now what we want to talk about in particular is we know more about organic compounds. We know that this combustion, what happens is we take our hydrocarbon, it reacts with oxygen. All of the carbon-carbon and the carbon-hydrogen bonds are broken, giving us just carbon dioxide and water. Now, the thing is, carbon-carbon bonds are very, very high in energy. They have a lot of energy in them. So when you burn it and you produce these carbon-oxygen bonds that are very low in potential energy, you've released a tremendous amount of energy as heat. That's why we burn these things for fuel, right? In our cars, for example. That's why we burn it for heat, from natural gas, all of that. Butane is used in camping, for example. Butane C4H10 reacts with oxygen to produce carbon dioxide and water. And of course, it produces a tremendous amount of heat energy. So that can be used to cook food or boil water, whatever you need to use it for. And again, it's portable, so that's why it's often used in camping. Okay, so here we go. Propane is a fuel often used in barbecues. Write a balanced chemical equation for the complete combustion of propane. So again, what you need to know is combustion reactions always follow the same route for these hydrocarbons. It's always going to be whatever your hydrocarbon is, plus oxygen, as a gas, and burns, right? And it produces water, CO2 as a gas, and water as a gas. And then all you have to do is balance the equation. So go ahead, give it a shot, pause the video here, and come up with your answer, and then we'll check our answers together when you come back. So go ahead, pause. Okay, and we're back. Again, all you have to do is basically sub in C3H8, where we put hydrocarbon before. So it's C3H8 plus O2 gives CO2 and H2O. The first thing that you want to do is go ahead and balance your carbons. If you have C3H8, then you need to have 3 carbon dioxides to balance the 3 carbons. Okay, next up, balance hydrogen. Now, all of a sudden, we're looking at the water here to balance that. If we have 8 hydrogens in the reactants, we need 8 hydrogens in the products. We need 4 water molecules to do that. Finally, let's go ahead and balance oxygen. Now note we have O2 as a gas, oxygen gas as our reactant. So we have 3 times 2, that's 6, plus 4 times 1 is total of 10. Oxygens in the products, To balance that out, we need 5 O2s in the reactants. And that gives us our balanced chemical equation. Okay, well, that takes us through the end of this discussion on alkanes. In our next lecture, we'll talk about alkenes, and then later on, we'll talk about aromatic compounds and how these are important for our, for understanding of biochemistry. But let's go ahead and we'll call it quits for now, and I'll see you again in the next lecture. Until then, bye-bye.